everybody, I wanted to walk through with you guys kind of what the VSEPR shapes look like if you could see them in a model. And I know that we looked at the simulation, but I'd like to just kind of show you what those models look like in 3D a little bit, and then go over how we can look at a model and figure out what kind of molecule it makes sense that that model is representing. So actually, this is similar to the table that you guys built when we did the simulation. If you haven't done that, make sure you go through and do that simulation. You've got to kind of cut and paste the pictures here. But what we are going to be doing is we are going to be talking about how all of these shapes relate to the number of bonds on an atom and the number of unshared pairs on an atom, or lone pairs as we call them. So like I had kind of said in our notes in the earlier sections, the VSEPR shapes, or molecular shape of a molecule, really depends on the center atom and what is attached to it. So when we are trying to figure out all of these shapes, the biggest thing is we've got to pay attention to the middle. And what we're going to kind of start off with is working our way from simple molecules to more complicated molecules. So the first thing that we want to talk about is we want to talk about a central atom here that has two electron dense areas. Now remember that an electron dense area can represent a bond, it can represent a double bond or a triple bond too, or it can represent a set of electrons that aren't attached to anything, and we call that a lone pair. Now, the reason why a double bond or a triple bond counts the same is because if I am drawing, let's say I have two atoms, and I have a single bond that connects them, that represents a pair of electrons that's stuck kind of between these two atoms. Okay, whatever we want to call these atoms. So we'll just color these in so that we know that they're an atom. Okay, so I've got two of these. This pair of electrons that's in the bond is stuck there. Now, if I have a double bond that has to exist to make this work, this second pair of electrons is also still stuck in between these two atoms. So when we talk about electron dense areas, what we're talking about is areas where electrons are kind of stuck in between atoms. And in this case, we have these two bonds here. If I have one bond or two bonds or three bonds, they're still going to be stuck in the same area between two atoms. So when we talk about electron density, they're still in the same area. So we are going to be talking about, in this one to begin with, the linear shape. And a linear shape is caused by a molecule that has two electron dense areas and no lone pairs. And when I talk about that, I am specifically talking about what's going on our central atom here. So carbon is my center. I don't want to pay attention to these oxygens. They're not super important. So all I am kind of considering is this and this. So when we think about the carbon has two areas where electrons hang out. It's got a double bond here and a double bond here. And because of that, if we think about how electrons are negative and they want to be as physically far away from each other as possible, kind of like magnets, the furthest away that they can be is 180 degrees. And so this molecule here represents a linear shape. This would be my carbon. These would be my electron dense areas, and these would be my oxygens. And this is our linear shape here, okay? It's called linear because it makes a line. Very clever naming. Now, when we talk about bond angles, we are talking about the angle from kind of here to here. So it's the carbon, or the oxygen to oxygen bond. In a linear molecule, it is always 180 degrees, and that's because they want to be as far away from each other as possible, these kind of two gray areas. So the farthest they can be apart is the exact opposite from each other. Okay, kind of sits flat. It's just a big line of molecules. You will also see linear molecules here when you have just two atoms together as well. So if I have two atoms, they're going to give me a linear shape, because if you think about it, if I have this and I take away and I just have two atoms in a bond together, those are only going to ever make a line as well. Okay, so that is if I have two electron dense areas. Moving on to three electron dense areas, if I have 3 bonds and no lone pairs on my center, I get a shape that we call trigonal planar. And here is an example of that. It's called boron trihydride. So boron is kind of a weird one. It only needs 6 electrons to have a satisfied outer valence shell. So boron doesn't need the octet, so we get this shape here. Okay. Now, what that looks like as far as a 3D rendering is this guy here. And that shape is called trigonal planar. And it's called trigonal planar because if you think about drawing sides on this, I have a triangle. And it's called planar because it's flat if you look at it. So if you look at this, all of my atoms lie in the same plane. So what I mean by that is if I would stick a piece of paper here, all of my atoms would be touching that sheet of paper. So it's called trigonal planar. Okay, now if you think about this shape here, the angle from this green to the center to the other green here, the farthest that these guys can push away is 120 degrees. And if you think about it, we think about a 360-degree circle. Each of these chunks here is 120 degrees, and we've got our circle. Okay, so that is if I have 3 bonds on the center atom and no unshared pairs. So if you look here, I've got no dots to worry about. Okay. Moving over, if I have 3 electron dense areas, but one of them is a set of dots, then I have a shape that we call bent. So if you think about looking at this picture here, I pay attention to my central atom and I pay attention to what's connected to it. So I've got a bonded area, I have a second bonded area, and I have a pair of dots, which are my lone pair. So that's when I have 3 dense areas, 1, 2, 3, but one of them is a lone pair. I get the shape that's bent, okay? So the bent shape here happens because if you think about it, if I have 3 electron areas here, 1, 2, 3, if I remove this bond and replace it with this little pink guy, which will represent a pair of electrons, I have this shape instead. So what happens is the shape stays kind of like trigonal planar. Like if you could imagine, I have this shape here, but instead of it having a bond, it has a pair of electrons, or if this makes it even easier to see, it's got nothing there. So this is just a pair of electrons that are not attached to anything, and the shape stays pretty much exactly the same here. However, the unshared pairs up at the top here, or the lone pair at the top, because it's not bonded with anything, takes up a little bit more room. So in the circumstance where trigonal planar has a bond angle of 120, this bent molecule here is a little bit less than 120 degrees because this electron pair here takes up a little bit more room. Okay? All right, now moving on to our 4 electron dense areas. This would be my first example of something called, or something with 4 dense areas but no lone pairs. So if you look at this picture, your first gut instinct might be to say that this is going to be a flat molecule too, and it's going to have bond angles of 90 degrees from like this carbon to hydrogen situation here. However, in 3 dimensions, you can actually have your elements. If you think about this, these elements don't actually lie in the same plane. They pop out into 3 dimensions and they produce this shape here, which is called tetrahedral. So what tetrahedral looks like is it looks kind of like a little pyramid with a little bond coming out of the top here. So if I rotate that around, you can see it's kind of like a little tripod with a bond coming out of the top here. And so what happens is, if I try to have these all sitting at 90 degrees, they are interacting with each other's pairs of electrons that are shared more than they want to, and this configuration gives them a little bit more space. So because it's got this kind of shape to it, it's got a weird angle. The angle that happens here is not 90, even though it looks like 90 in 3 dimensions, the bond angle is 109.5 degrees. So with your tetrahedral molecules, when you have 4 electron dense areas, all of these have bond angles of 109.5, okay? So this is my first one with no lone pairs. if I go to an example that has a lone pair, I still have 4 electron dense areas around my center. So I've got one bond here, one bond, another bond, and a pair of electrons. With these all, and I should back up to, we'll say this one. Again, we're only paying attention to the center. So whatever is attached to these oxygens on the outside, not important. We only care about the center. So back to this guy here. What you can imagine is that if I have 4 electron dense areas, my molecules still look like a tetrahedron, but the top is popped off. So I'm missing this little top area here. So instead of having a bond coming up here like I did before, now I have nothing, like that. Okay. This molecule has the shape of trigonal pyramidal. And the reason why it's trigonal pyramidal is because it looks like a triangle. Okay. And if we put it flat, it looks like a little pyramid. So if I were to put a sheet of paper here, this is going to sit above it like a little pyramid. Okay. Now, because this electron pair here takes up a disproportionate amount because it's not bonded, it's not stuck between 2 atoms, it just gets to kind of move around up here, it's going to squish these bonds a little bit closer to each other. So each of these bonds are a little bit less than 109.5. Now, I don't need you to know exactly how many degrees they are less than 109.5, but they are less than 109.5. All right, and lastly, if I have 4 electron dense areas, but 2 of them are lone pairs, then I get a bent molecule. This is H2S. And if I highlight the stuff going on around sulfur, I've got 2 bonded areas and 2 pairs of electrons that aren't attached to anything. So that's what I'm talking about when I have 4 dense areas and then 2 pairs of electrons, okay, or 2 lone pairs. In this case, they start off with that tetrahedral shape. So if I think about this as my tetrahedral shape, 2 of these, instead of being bonds, are missing, and they are technically occupied by a pair of electrons up here and a pair of electrons up here. But when I look at the actual molecule, it has a shape kind of like that one before that's called bent. So this is a bent molecule as well. But what's different about this one is the bond angle. So the bond angle on this guy here is less than 109.5 for the same reason the other ones are less than. It's because those electrons take up a little bit more room. Now somebody might say, well, these are on opposite sides, so shouldn't that cancel out? On paper, it looks like that, but in reality, those electron pairs, if I add them in here, okay, these electron pairs actually aren't sitting flat, so they're not on top and on bottom. They're actually in the shape of the tetrahedron. Okay, so what we're going to ask you to do is we're going to ask you to take a look at some examples, and then you are going to do a little bit of practice to identify them. And again, it's the center atom that matters. So for instance, I'm going to bring my examples over here. Okay, and if you feel good about this, you can stop watching the video and go right to the practice. But if you want a little bit more practice, we'll give it to you. So if we start here with PI3, again, I'm only paying attention to the center. I'm ignoring all this stuff out here. Highlight or mentally highlight what is attached to it. So if you look, I've got 4 things highlighted. So I have 4 electron dense areas. One of them is a lone pair. So that means that my shape is going to be trigonal pyramidal. And I'm just going to put trig pyramidal to save a little time. And my bond angle on this is going to be less than 109.5. And if you want, you could write that, you know, if it would let me. Okay. All right, so that is that. Looking at H2O here. Highlighting or mentally highlighting my electron dense areas. I have 4 dense areas. 2 of them are lone pairs, so I'm going to have a bent shape, and my bond angle is going to be also less than 109.5 degrees. Okay. Moving on to this one, OCH. Again, only what's connected to my center. Okay. I have 3 dense areas and all of them are bonds. I don't have any dots on my central atom at all. So if I look at that, then 3 dense areas, no lone pairs, means that I have the shape of trigonal planar. And my bond angles are 120 degrees. And so hopefully you can kind of get the hang of it. Now, once in a blue moon, you are going to encounter the 2-centered atom. So let's say I have CH3 and then C and an O and an H like this, okay? Now, in this case, I have a bunch of different potential VSEPR shapes because I have lots of different centers. So I could ask you the VSEPR shape of this carbon. And this carbon here has 4 electron dense areas and no bonds. So this carbon is going to be tetrahedral. Okay? But I could also ask you a question about this oxygen. So this oxygen acts as kind of a center. And if I highlight that and smear my pen all over the place, I have 4 electron dense areas, but now 2 of them were dots. So if I've got 2 sets of dots and 2 bonds, I have a bent shape. And that bond angle is less than 109.5 degrees. Okay. And then if I want to take a look at this carbon, I could do that too. So in this carbon, I'll highlight my dense areas. Okay. And on that carbon, I have 3 dense areas, no lone pairs. So that is trigonal planar. So you can have a bunch of different shapes within this molecule. So if you think about this one as kind of a 3D shape, this one is shaped like a tetrahedral, which I kind of destroyed. Woo, hold on. Trying to work under pressure. Okay, so this would have this shape, but then I would also have it attached to something that's kind of like a trigonal planar. As I drop my molecules on the floor. So if you think about it, I would have one that's kind of trigonal planar. So like this area is tetrahedral. This area isn't tetrahedral. It's kind of this trigonal planar shape. So I've got a flat part here. So like these guys are in the same plane, but these guys aren't. And then over here, I would have it bend that way. So the molecules get very complicated as we go along. So your homework or your practice is going to be to just look at molecules and identify the shapes and identify the bond angles. All right? Good luck.